Welcome to the FTCS tool webinar, Fault-tolerant Control Strategies for Physical Anomalies Affecting the SCADA System. This tool deals with physical threats at operational level. My name is Jordi Meseguer and I am researcher and project manager at Cetaqua Technical Center. This tool deals with the problem associated with the disruption of water supply services and low water pressure conditions due to either planned interruptions or due to unexpected events like pipe bursts. This problem impacts in the customer and the network because mainly there will be non-supply and demand and some of them will be affected by low water pressure conditions. Additionally, new pipe failures might occur due to wrong valve operations during the pipe failure repairing process. This is the typical response plan when this problem occurs. First, to detect the faulty assets and assess the impacts, then isolate the failure event location to allow repair of the impacted assets, and then to define a temporary and emergency interventions to recover the water supply service. Mainly, this tool deals with this third step, aiming to optimize this process of defining emergency interventions to recover the water supply services in order to shorten the recovery time to improve the quality of the recovered service and reduce the operational cost of the mitigation plan. This tool applies to physical threats at operational level, as I mentioned. The main focus is set on the recovery phase once the failure is isolated. The tool optimizes the process of selecting the needed network interventions in order to minimize the negative impact of the failure isolation. The tool deals with those alternative water supply options that in normal conditions are not used. Additionally, deals with events and anomalies located in the transmission network. This tool can be seen as a recommendation system supporting decision-making to choose the best network reconfiguration to recover the water supply service. The tool is a simulation environment, and in the STOPIT project, the main target is to validate the methodology associated with this tool. The main requirements associated to this tool are the following. So, the hydraulic model of the network, considering the existing alternative water supply options, is needed. So, in this hydraulic model, the transmission network must be represented and the distribution network must be represented in a simplified manner. This is DMAs are represented as demand nodes. Also, from the SCADA, hourly forecasts of the demand for the next 24 hours are needed. And also, the operational strategies applied to the network actuators in normal conditions are also needed. This is for pumps and remote control valves. The tool integrates two commercial tools. This is GAMS. GAMS is a commercial software that allows rating optimization problems, offering a library of optimization solvers. And Piccolo. Piccolo is a hydraulic modeling simulation tool developed by Suez Group that is being used widely in Suez water utilities. Piccolo is used as a virtual reality to assess the performance of the computed operational strategies, and also other modeling tools could be used using proper connectors. Okay. Every scenario related with this tool focuses on recovering the pressure at the DMAs or demand zones degraded by the shutdown of a part of the network. To define a scenario, the user has to notify pipes that need to be isolated to proceed with the repairing of the anomaly or plant maintenance work. To to notify the existing alternative water supply options associated with the DMAs or demand zones. What the FTCS tool computes as a result. At the distribution network level, the tool computes the selection of the alternative water supply options needed to recover pressure at the DMAs or demand zones during the scenario. At the transmission network level, the tool computes new strategies, if needed, for pumping groups and remote control valves to keep tank water levels within the safety limits and to recover pressure at the affected transmission network. What the tool does to compute the results. First, to update the hydraulic model with the notified isolated pipes and available alternative water supply options. Then, to generate optimization equations for GAMS using the hydraulic model structure. Third, to run the updated hydraulic model to generate the initialization files for GAMS considering the isolation of those pipes notified by the user. Fourth, to run GAMS to solve the optimization problem. Then, to update and run the hydraulic model implementing the solution computed by GAMS. And finally, to compare network dynamics computed by the updated hydraulic model with estimations obtained solving the optimization problem. So, regarding the properties of this tool is developed in Python, integrating Piccolo and GAMS. There is no user interface nowadays, since the main goal in Stopit is to validate the methodology. Zetaqua and IBS Barcelona are validating the methodology using real and now scenarios. So, in this box, you can see the main features of this tool. First, related to the scenario definition, as we explained. Then the automatic generation of the optimization equations. Third, the generation of the initialization files for the optimization to solve the optimization problem. Then run the optimization solver, and finally to show the results using the hydraulic model. All these features are integrated with Piccolo and the optimizer GAMS. In the following slides, we will explain a scenario example. That the description of this network is the following. So this network consists in 8 DMAs represented as demand nodes. You can see here the DMAs. This is these nodes. 2 pressure management zones, 1 and 2. 2 tanks and 2 pumping stations located in these areas, and 32 alternative connections that are these blue lines that connect one DMA with another DMA, or one DMA with different points of the transmission network. As I mentioned, in brown is the normal configuration of the network given by these transmission lines, and then these other lines are the inlets to the DMAs. And in blue are the alternative water supply options that exist in case that anomaly is affecting the transmission network, and can be used in order to recover the pressure at the DMAs. In this example, an anomaly occurs in this transmission line. So it must be isolated, closing these 2 valves, and this impact in the water supply of this DMA, because the water cannot be supplied using the normal inlets of this DMA. So different alternative water supply options must be used in order to recover the water supply service at this DMA. There is 9 alternative water supply options. Then we run the tool, and the tool proceed in order to select which are the best water alternative supply options in order to recover the water supply, the pressure in the DMA, and also taking into account using the minimum water alternative supply options, and if possible without modifying the default strategies that apply to the pumping stations. In this case, so the affected DMA is DMA 7, and the pressure was recovered to 129 meters, being 130 the reference, and here alternative, the water supply options 1 and 6 has been used in order to recover the pressure. So at the end, the valves associated to these water alternative supply options are fully open during the scenario. So the current status of the tool. So the methodology behind this tool is being validated using real and known scenarios by FTCS and IWS de Barcelona. Currently, the tool is targeting incidents in the transmission network on mains. The network has to be represented in a hydraulic model, simplifying the distribution part, representing DMAs or demand zones are demand nodes. The methodology and tool is general to be applied to other networks, just with reasonable adaptations to cover new situations. Thank you very much to listen this webinar of the FTCS tool. Here you can see my details, and do not hesitate to send me any question or request me further information regarding this tool. Thank you very much.